This is week 11 of the Applied Thermodynamics course. Previous week we saw about refrigeration, how the compression refrigeration system works, and vapor absorption refrigeration systems, so how they work, and we solved some numericals on those. So the next part of what we see today is now we have refrigeration. So we need to study air. So we use refrigeration mostly for refrigeration and air conditioning. So in air conditioning, you need to air conditioning is basically you condition the air. So you condition the air such that you will feel comfortable. It may be a hot climate, and it will not. It doesn't mean that you just reduce the temperature. What happens if you are in a region very close by to sea? So in that case, what will happen? Or take suppose Chennai or any other where you will feel humid. There will be also a temperature, and also you will feel humid. So this is because of the water vapor in there. So in that case, for you to feel more comfortable, you need to condition the air such that you make it cool it or heat it to a temperature where you feel comfortable, and then also where you add water or reduce water vapor in the air. So that study of moist air, it what will involve in this week. Basically, human feel more comfortable near 24 degrees Celsius and 50% relative humidity. So that is the comfort region, and there's a band of range of region where you will feel comfortable. And people use condition air conditioning with also normal conditioning. You add some fresh air with the all air which is being cooled to to make into account that enough oxygen is present in the in CO2 level doesn't exceed a limit. Basically, it's close to 1000 ppm, where you will start feeling headaches and everything. So to avoid that, they'll add some fresh air from outside to the air conditioned room. So that like a mixing of two streams. So we'll see some numericals on those also. So these are various techniques which people use to, in air conditioning. So this all comes under the psychometric process. So we'll see how this process are done. We'll see some numericals on those, and the basic idea I'll start with the basic idea on the psychometric chart. So the psychometric chart, you see you have on the x-axis you have dry bulb temperature. So dry bulb temperature is your temperature of the air, which is if you put up a thermometer, you will get that temperature. So that temperature is your dry bulb temperature. And on the y-axis you have a specific humidity. The specific humidity is the humidity mass of water vapor which is present in air. So that specifies the specific humidity. So per kg of air, if you take a dry air, how much mass of water vapor is present in there. So that signifies your specific humidity. So that if you see that specifies the moisture content also. So and here there are some constant lines. If you see this vertical line, so the vertical line will signify that the dry bulb temperature is constant. And if you see an horizontal line, it says that your moisture content is constant. And if you there are lines where see there's a curved line here, so that signifies a saturation line. So saturation line is where your air is saturated, so it cannot take any more of water in there. So it is already saturated, it cannot take any more water. So that is the saturation line. So there's another term called as relative humidity. So this relative humidity is how much of water vapor is there with respect to the saturated case. So that signifies your relative humidity. So this saturation line will have 100% relative humidity, and other there's a relative humidity line shown. So these are constant relative humidity lines. And then in the saturation line, that lies the dew point temperature. So if the temperature reaches this point, it's says that it's in saturated condition, and if water can condense. So if you cool at this temperature, your water in the air can condense. So that is your dew point temperature. And there is something called as the wet bulb temperature. So this wet bulb temperature is similarly a case to find out the temperature at which your air will be saturated. So if you have a dry air around you, what you do is you dip a small cloth or some cotton or something within water. You put it in the thermometer bulb, and what will happen is air will pick up this water. It will take away some water vapor, and in that case water while evaporating, it will take away some heat from the water in the cloth, and the temperature of the cloth will go down. So correspondingly what will happen, it will reach a case, a steady state, where the temperature is at a saturated condition. So in that case your temperature is called the wet bulb temperature, and that line, wet bulb line, is temperature, it remains, wet bulb temperature will remain constant. And also you will have some relative enthalpy lines passing through, which will be similar to the wet bulb. So these are the major constant, and also a specific volume lines can also be found in the cyclotropic chart. So similarly, if you see, there are some processes which is shown on the right side. You see, O is the center point, and then OA is your heating case. So in that case what happens, your specific humidity will remain same, but you're just heating the air. You're not adding any water, or you're not removing any water vapor from there. So that is called as sensible heating. And the other process opposite of it, OB, is your sensible cooling. In that case you are not varying the specific humidity of the air, but what you're doing is you're cooling the air, you're bringing down the temperature. So if you see, the dry bulb temperature reduces or increases based on the process, but your specific humidity is constant. So that is sensible heating or cooling. If you see OC and OD, it's just humidification and dehumidification. So in that case what happens, your temperature will remain same, but you are adding water vapor to that. So in that case OC is humidification. So you can add it till you saturation. So that is the maximum amount of water vapor which you can add. And OD is the dehumidification, and you can remove till you make it a dry air. So that is OD. And then other process which is OG, which is you have humidification with cooling. You cool the air and you humidify it. And then OF is cooling with dehumidification. So in that case you remove air and cool. So that's the process. So OE is humidification with heating, so like adding steam or something, and OH is dehumidification with heating. So these are the major processes which you will come across in a cyclotropic process. So moving on, we'll see some MCQs and numericals on the processes. So starting with, it says the wet bulb temperature at 100% relative humidity is dash of dry bulb temperature. So the wet bulb temperature will be equal to the dry bulb temperature at 100% relative humidity. So if you see here, the wet bulb temperature, this is 100% saturation line. So this point and the wet bulb line and your dry bulb temperature, this both will merge here at the saturation line, and this temperature, the dry bulb temperature and wet bulb temperature will be equal. So what it says is, your wet bulb temperature is already says that your water vapor is saturated, and you cannot add any more water. So that's the minimum temperature which you can reach while adding water vapor in there. So that's what it signifies. So at saturation condition, this temperature both will become equal. So hence it's equal to. So the next is the specific humidity decreases during cooling and dehumidification process. The specific humidity decreases during cooling and dehumidification. Okay, so as we have seen already, there is a sensible cooling and humidification or dehumidification. The dehumidification, you remove latent heat, but in sensible cooling, you remove sensible heat. So the question itself says it's cooling and dehumidification. So cooling, it will only bring down temperature, but dehumidification will bring down the water vapor in the air. So your water specific humidity is nothing but mass of water vapor in the air divided by mass of air. So if humidification happens, your water vapor in the air goes down, so your specific humidity will also go down. So this statement is true. So specific humidity will decrease. So moving on, in dehumidification will take place along with cooling if moist air flows over cooling coil whose mean surface temperature is below the dash of the entering air. Just saying cooling and dehumidification. The process again cooling and dehumidification. They're saying the cooling and dehumidification process can occur if moist air flows over cooling coil. So moist air is just water vapor plus air mixture, dry air mixture. So if this flows over a cooling coil whose mean surface temperature is below that of dash of the entering air. So the answer is dew point temperature. So we, as I already previously told, dew point temperature is a point where temperature at which the water will start condensing. So if the water starts condensing, and then the specific humidity in the air will go down because it's losing water vapor. So this is equivalent to a dehumidification process. And as the surface temperature is lower, so dew point temperature will be lower than your air temperature, so it will cool in the process, it will cool also. So hence it's a cooling and dehumidification process. So your mean surface temperature will be below the dew point temperature. So next is, in case of cooling tower, water is cooled by the process of evaporation. It's a true or false statement. So in a cooling tower, water is cooled by the process of evaporation. So the answer is true. So if you see in a cooling tower, what happens is you take any process industry or anything, you have water which is being used and you want to bring down the temperature of the water. So you cannot directly dump it into reservoirs or something. So in that case, what you do, you have to bring down the temperature first, and to do that, what will you do is you will use a cooling tower. So you will the high temperature water will be it will sprayed over, and from bottom you will pass air. So what will happen is the water vapor, and when it comes with contact with air, some of the water vapor will evaporate, and in the process what will happen is that evaporation, it will take heat from the water droplet itself, and it will bring the temperature of the water droplet, and the water is collected at the bottom again, and it can be reused or it can be dumped in water. So in this case, if you see, there is evaporation taking place when the water droplet is coming in contact with the air, and so the statement is true. The next question is, evaporative cooling takes place nearly at constant dash. So evaporative cooling takes place nearly at constant wet bulb temperature. So this is evaporative cooling. So this process, what will happen is, so the evaporative cooling, you have evaporate. So your water will evaporate, and it will the specific humidity of air will go up, and in the process you're also cooling the air. So it follows OG path. Uh, so it's a cooling and humidification process, and in this process what will happen is this wet bulb line, it will follow this wet bulb line. So the temperature of the humidification process, in that process what will happen is this wet bulb temperature will remain constant throughout the process. Because you are humidifying air, and it can maximum it can reach is the wet bulb temperature. It cannot go below wet bulb temperature. So at any point of time, even though your dry bulb temperature may be different, but your wet bulb temperature will remain same, because as I told previously, wet bulb temperature signifies you have reached a saturated vapor condition. So that will remain same throughout the process. So your wet bulb temperature will remain constant. Next question is, the difference between dry bulb temperature and wet bulb temperature is known as dash. So it is called as wet bulb depression. So the difference between the dry bulb temperature and wet bulb temperature is called as wet bulb depression. The next question is, in cooling tower, the term approach is the temperature difference between the inlet temperature of water and wet bulb temperature of inlet air. So approach temperature is the temperature between the water temperature and the wet bulb temperature of air. This statement is true. As we already see that wet bulb temperature will remain constant, so this difference between the temperature is called as the approach. So the statement is true. Next question is, the minimum temperature to which moist air can be cooled under ideal condition in spray washer is dash. So the minimum temperature to which moist air can be cooled moist air can be cooled under ideal condition in spray washer is, so we saw what this in air washers, what can happen, you can have cooling, humidification, and good humidification and heating. The other combination of process can take place based on the water temperature. But in any of the case, what will happen is the air can be cooled in a cooling process, it can be cooled only to the wet bulb temperature. So after that, what will happen is your air is already saturated, it cannot take any more water vapor, so it has reached saturation condition, and that condition is called as wet bulb temperature. It cannot go any below. So the answer is wet bulb temperature. So the next question is, for a typical sample of ambient air at 35 degrees Celsius and 75% relative humidity and standard atmospheric pressure of 1.013 bar, the saturation pressure of water vapor at 35 degrees Celsius is 0.056 bar. The amount of moisture in kg per kg of dry air will be approximately. So what it says is, we need to find out the amount of moisture present in the dry air per kg of dry air. So you know that your ambient air is at 35 degrees Celsius, this is your dry bulb temperature, and they say it is at 75% relative humidity. So you know dry bulb temperature and relative humidity, and you know the atmospheric pressure, and they also given that the saturation pressure of water vapor at 35 degrees Celsius is 0.056 bar. So we'll see how to solve this. So what is known is your dry bulb temperature 35 degrees Celsius, you know relative humidity 5 or RH, however you can denote it. 5 is 75%, your atmospheric pressure is 1.013 bar, and your saturated pressure at 35 degrees Celsius is 0.056 bar. So we know that relative humidity is nothing but saturated vapor pressure divided by vapor pressure of water vapor divided by saturated pressure. So we know that relative humidity is 75%, so 0.75 equals PV by your saturated pressure 0.056. So PV will become equal to 0.042 bar. So we now know your vapor pressure. Now we can calculate relative humidity. So so specific humidity, we can calculate specific humidity omega equals 0.622 into PV by P minus PV. So omega is nothing but mv by m dot a, or m mass of dry air. So mass of dry air is nothing but mass of the total air mixture plus minus mass of vapor. So that can be converted into pressure, and this terms comes because of your molecular weight. So then it can be reduced to omega equals 0.622 into PV by P minus PV. So substituting PV, which we have calculated, and we know the atmospheric pressure 1.013, and using this we can find out specific humidity. So that will be equal to 0.027 kg per kg of dry air. So which was asked. So moving on, we'll see another problem. So here the ambient pressure, temperature and relative humidity of air at location are 101 kilopascal. So ambient pressure and temperature is 300 Kelvin, relative humidity is 70%. The saturation pressure of water vapor at 300 Kelvin is 3.6 kilopascal. So similar problem, we need to find out specific humidity in grams per kg of dry air. In previous problem it was asked to find in kg per kg of dry air. Here it's gram per kg of dry air. The process is similar. So you know atmospheric pressure, you know temperature, you know relative humidity, you know saturated pressure. So similarly, relative humidity is PV by Psat. So you know relative humidity, you know Psat. Substituting, we'll get PV, which is 2.52 kilopascal. So omega is nothing but specific humidity is nothing but 0.622 into PV by P atmosphere minus PV. So omega is 0.0159 kg per kg of dry air. So this will give in kg. So now for finding getting answer in gram per kg of dry air, you need to multiply by 1000. So this will give me omega as 15.9 grams per kg of dry air. Okay. So the next problem is, we have 1 cubic meter of H2 at 1 bar and 25 degrees centigrade, or is mixed with 1 cubic meter of nitrogen at 1 bar and 25 degrees Celsius. For the mixture at the same condition, find. So we have H2 and N2 with both 1 cubic meter and both at 1 bar and 25 degrees Celsius. For this mixture, find out mole fraction of components, partial pressures of components, mass fraction of components, molecular weight of the mixture, gas constant of the mixture, and volume of the mixture. It's just a similar problem, but instead of taking water vapor and air, we are taking hydrogen and nitrogen. So the molecular weights of hydrogen is 4 and nitrogen is 28. So gas constant for each of it is hydrogen will be 8.314 universal gas constant divided by molecular weight, which will come out to be 2.077. Similarly for nitrogen it's 0.2967, and the masses we can calculate using ideal gas equation. So M1 is P1 V1 by RT1. We know pressure is 1 bar and volume is 1 cubic meter, and divided by R we have found out. We know temperature 25 degrees Celsius to 298. So we can find out mass of hydrogen will come out to be 0.1616 kg. Similarly for nitrogen, we is 1.131 kg. So total mass will become summation of 0.16 mass of hydrogen plus nitrogen is equal to 1.2926 kg. Using this, we can find out number of moles of hydrogen and nitrogen. We find out mass of hydrogen divided by molecular weight. Will give me moles of hydrogen. So that will come out with 0.0404, and moles of nitrogen is 0.0403. So the total number of moles is 0.0807. So now we have found out the total number of mass and moles. So we can find out mole fraction. So mole fraction hydrogen is nothing but moles of hydrogen divided by total number of moles. So that will come out to 0.5. And similarly for nitrogen is 1 minus hydrogen, or we can find out using that will come out to be 0.5 again. So it's close to 0.5. The small difference, but it is close to 0.5. And the partial pressures are E1 equals to Y1P. So using Dalton's partial pressure, we can find out mole fraction into the total pressure will give me the partial pressure. So each of it will be 0.5 bar. The second, to find out the mass fraction. So mass fraction is nothing but mass of hydrogen divided by total mass. That will give me 0.125. And similarly for nitrogen, it will give me 0.875. That's the mass fraction. So molecular weight of the mixture. So molecular weight of the mixture we can find by mole fraction into molecular weight, summation of that. So or can find out moles into molecular weight divided by total number of moles. So mass of molecular weight of the mixture will become Y1 into M1. So hydrogen molecular weight into hydrogen mole fraction. Same similarly for nitrogen. So this summation will come out to be 16.01. So this is the molecular weight of the mixture. So gas constant of the mixture is similarly universal gas constant divided by molecular weight, which we have found out. So 8.3143 divided by 16 will come out to be 0.5193 kilojoule per kg Kelvin. Now for volume of mixture we can just add both the volumes because both are at 1 cubic meter. So we can add, we can make it 2, it will come out with 2 meter cube, or we can find out using mass into MRT by from ideal gas equation. So MRT by 2. So mass is we have calculated the total mass into R we have calculated, so into T divided by pressure. So this will also comes out to be 2 meter cube. So this is similar to V1 plus V2. So both were 1 meter cube. So if you add, you will get 2 meter cube. So that both the values are same. So the next question is, in a dew point apparatus, a metal beaker is cooled by gradually adding ice water to the water initially at room temperature. So you have a dew point apparatus. So in that you have a metal beaker which is cooled gradually by adding ice water to the water initially at room temperature. So the moisture from the room air begins to condense on the beaker when its temperature is 12.8 degrees Celsius. So initially you have a metal beaker, or just similar to the case of having pouring cold water inside a glass. You have a cold drink or something, you pour it in a glass, you see there is a condensation outside. So it's a similar kind of experiment. What you have a metal beaker, you have some water inside it. Now you are pouring ice water into the water which was initially at room temperature. So now this both water will mix and it will come out to some temperature. So when this temperature is 12.8 degrees Celsius, it is found that the water condenses on the outside of the beaker. So now if the room temperature is 21 degrees Celsius and the barometric pressure is 1.01325 bar, find the partial pressures of water vapor in the room air and parts by mass of water vapor in the room air. So what is the mass fraction of water vapor in the room air and the partial pressure of water vapor room air? So that's what has been asked. So we know partial pressure of water vapor at dew point temperature, which is 12.8 degrees Celsius, is 1.479 kilonewton per meter square. So using that, and partial pressure of dry air is total pressure divided by minus the vapor pressure, so that will come out to be 99846 Newton per meter square. Now specific humidity is nothing but mass of vapor divided by mass of dry air. This also can be expressed in terms of pressure as 0.622 into vapor pressure divided by partial pressure by of dry air. So we know both the values. On substituting, we get specific humidity as 0.009214. So now we can find out parts by mass of water vapor in the total mixture. So mass of vapor is nothing but omega into ma. So and ma can be expressed as mi minus mb. So writing expression for m in terms of mv by ma, we will get omega by 1 plus omega. On substituting the specific humidity values, we will get this vapor mass fraction as 0.00913 kg of water vapor per kg of mixture. So we have found out both. So here we have used 12.8 degrees Celsius because at dew point temperature you are started condensing, so that means your water vapor is at saturated condition at that temperature. So your pressure you can find out easily what is the vapor pressure at that condition, saturated condition. The same vapor pressure you will have it in 21 degrees Celsius as well. So that's why to find out the vapor pressure we use dew point temperature. So the next question is, a mixture of dry air and water vapor is at a temperature of 21 degrees Celsius under a total pressure of 736 mm of Hg. The dew point temperature is 15 degrees Celsius. So here here you have a mixture of dry air and water vapor which is at temperature of 21 degrees Celsius. Your dew point temperature is 15 degrees Celsius and your total pressure is 736 mm of Hg, or room normal pressure 1 bar. So here you need to find out partial pressure of water vapor. You need to find out partial pressure of water vapor, relative humidity, specific humidity, and specific enthalpy of water vapor by 3 methods. So here 3 methods, in sense you find out A, B and C, all 3 points. So water vapor, here it's the vapor region, it's a liquid region, waterless vapor region. So here water vapor, you need to find out enthalpy at these 3 points, A, B and C. And fifth is to find out enthalpy of air per kg of dry air, and 6 is specific volume of air per kg of dry air. So we'll see how to solve this. So first is we know your dew point temperature is 15 degrees Celsius. So at 15 degrees Celsius your partial pressure of water vapor is, so this will be at this point C. Dew point temperature, so this will be at this point C. So TD is the dew point temperature and T is the dry bulb temperature, and these lines are constant pressure lines. This is in TS curve, and this will be constant pressure lines. So if you see in the previous problem, we find out vapor pressure. We can instead of at 21 degrees Celsius, we found it at 12.5 degrees Celsius, the dew point temperature. So if you see, that was the saturated pressure which we calculated. And if you see, it will go along this pressure will remain constant, and that the vapor which is present at room temperature will also have the same vapor pressure as at the saturated temperature or the dew point temperature. So in this case, here the dew point temperature is 15 degrees Celsius. So at that temperature, the corresponding vapor pressure is 12.79 mm of Hg, or 1707.5 Newton per meter square. So that's what does partial pressure of water vapor. So we have found out partial pressure of water vapor. So here it will remain same. So partial pressure of water vapor is 1707.5 Newton per meter square. Now saturation pressure of water vapor at 21 degrees Celsius dry bulb temperature. So to find out relative humidity, so if the air should become saturated at 21 degrees Celsius, so then the relative humidity will become 100%. So in that case, what will happen is the saturated water vapor pressure at 21 degrees Celsius will be 2489.8 Newton per meter square. So your relative humidity now is PV by P saturated. So PV we have already found out 12.79 mm of Hg, and saturated pressure is 18.65 mm of Hg. So this will give me 68.58%. So this is the relative humidity of the air. Now to find a specific humidity, we use the relation omega is 0.622 PV by PA. So we know vapor pressure, we know air pressure, we can easily find out. You know total pressure minus PV. So the vapor pressure is 12.79 divided by 736 is the total pressure minus 12.79. So this will come out to be 0.011 kg of water vapor per kg of dry air. So this is the specific humidity at this condition. So the next is to find out the latent heat of vaporization of. You need to find out the enthalpy of water vapor, specific enthalpy of water vapor by 3 methods. So C, A, B, and B. So initially, what we'll see is we'll find out your latent heats at 15 degrees Celsius, which is this dew point temperature, and at room temperature. So at 21 degrees Celsius. So both are 2452 and 2466.2 kilojoule per kg. So now for Hc, we can easily find out. Now if you take the datum as 0 degrees Celsius, from 0 degrees Celsius to C 21 degrees Celsius, that will be sensible heating. So you heat it sensibly, so it is 4.1868 into 21. 4.186 is Cp of water. So Cp of water is 4.186 into your temperature difference, 21 minus 0, so 21 plus your latent heat at 21 degrees Celsius, 2452. So that will give me 2540, which is the enthalpy at point C. So enthalpy at point A, we can easily find out by similar method. So initially there will be sensible heating of water, then latent heat, and then sensible heating of steam or water vapor. So 4.186 into 15 minus 0 because dew point temperature, 15 minus 0. Then latent heat of at 15 degrees Celsius, which is 2466.2 plus 1.88 into 21 minus 15. So that is superheating of vapor. So that will come out to be 2540.3 kilojoule per kg. Now at point B is latent heat at 0 degrees Celsius, which is 2501 plus superheating of vapor, so 1.88 into 21 minus 0. So that will come out to be 2540.5. So if you see why we did this is, if you see, you do any process, the enthalpy of water vapor along if you do any along any process, you see the enthalpy is close. It's not different. It's in point some different. So that is negligible compared to the magnitude of the specific enthalpy. So in whatever process you can find out water vapor, and that enthalpy will be close, value will be same. Next is to find out enthalpy of air using the value of specific enthalpy of water vapor from the relation. So now the enthalpy of air plus water mixture is enthalpy of air plus your specific humidity of your air into enthalpy of vapor. So m dot v, so it's nothing but mass in enthalpy balance. So m dot into h equals m dot a into ha plus m dot v into hp. So and if you differentiate by m dot a, it will be, you can find out. So here enthalpy of air is nothing but Cp into delta T. So Cp 1.005 into delta T is 0 to 21. So there you can find out enthalpy of air plus the specific humidity we have already found out, which is 0.011 into Hv is 2540.5, which we have already found out. So this will give me that enthalpy of air mixture is 49 kilojoule per kg of dry air. So now specific volume of air for 1 kg of dry air or 0.01 kg of water vapor is, so we can use ideal gas equation. So dA is Ra T by Pa. So this is specific volume, so RT by T. So Ra is 287.3 for air into temperature divided by pressure. So here 723.21 is the P minus PV into conversion to Newton per meter square. So this will come out to be 0.875 meter cube per kg of dry air. So next question is, we need to calculate humidity ratio, dew point temperature, density and enthalpy of atmospheric air when the dry bulb temperature is 35 degrees Celsius, wet bulb temperature is 23 degrees Celsius, and your pressure is 750 mm of Hg, and relative humidity is 36%. So we'll see how to solve this. So relative humidity is fairly simple. Phi is PV by P saturated. P saturated. So for 36%, and 35 degrees Celsius, your saturated pressure is 42.2. So using that we can find out PV, which will come out to be 15.818. So using PV, and we can find out humidity ratio. So humidity ratio is 0.622 PV by P minus PV. So substituting PV, we can find out specific humidity ratio as 0.01285. So dew point temperature is nothing but, we know PV, when this is at saturated pressure, the corresponding temperature, so saturation temperature corresponding 15.18 mm of Hg is 17.7 degrees Celsius. So that is the dew point temperature. Now we can find out partial densities. So density is P by rho R, P by RT. So we can find out density of air substituting pressures of air 750 minus 15.18 into conversion divided by R gas constant into temperature. So it will come out to be 1.1086 kg per meter cube. This is the density of air. Similarly, for water vapor is 0.0143 kg per meter cube. So now, so the density of moist air is rho is rho A plus rho V. It will come out to be 1.1229 kg per meter cube. Here, because rho is rho A plus rho V, because mass of total mixture is m dot, it will be m dot A plus m dot V, and your volume is constant. So both the air, for air and water vapor, the volume is same. So if you divide it by volume, it will get m dot by V equals m dot A by V plus m dot V by V. So it will come out to be density rho equals rho A plus rho V. So next question is enthalpy. Enthalpy is 1.005 T plus omega into 2500, which is your latent heat of water vapor at 0 degrees Celsius, plus 1.88 into T. So 1.88 is Cp of water vapor. So your enthalpy will be, temperature is dew point temperature, dry bulb temperature. So 1.005 into 35 plus your omega, we have already calculated specific humidity, 0.01285 into 2500 plus 1.88 into 35. So this will come out to be 68.15 kilojoule per kg of dry air. So we have found out all density, enthalpy and humidity ratio. So we'll see, move on to the next problem. So this is a cooling and dehumidification of moist air. So moist air at standard atmospheric pressure is passed over a cooling coil. So show this process on a psychometric chart. Then determine the amount of heat and moisture removed per kg of dry air. The inlet and exit states are given. So inlet state is 30 degrees Celsius of dry bulb temperature and 50% relative humidity. Similarly, for exit is 15 degrees Celsius dry bulb temperature and 80% relative humidity. So we know inlet and exit conditions. So this is a cooling and dehumidification process. You have a cooling coil, so you are passing a refrigerant and you are passing air over it. So air is at 25 degrees Celsius and 50% relative humidity at the inlet, and when it passes through the coil, water vapor will condense and it will get accumulated at the bottom. So and here the vapor which coming out, air will have less water vapor and it will lose some heat, so it will cool. So this is at 15 degrees Celsius and 90% relative humidity, sorry 80% relative humidity. So that's a typo, which is 80% relative humidity. So similarly, psychometric charge, you can plot at 30 degrees Celsius, so 25 degrees Celsius, here it's 25 degrees Celsius and 50% RH, and similarly 15 degrees Celsius and 90% RH. You can join that line, and if you extend that line, you will go meet in the saturation curve. So this point will be your dew point temperature. So at that point you will start forming drops of condensation. The water vapor will start condensing. So if your cooling coil is less than your saturated or adiabatic dew point temperature, your cooling and dehumidification process will happen. So starting with we need to find out the amount of heat and moisture removed. So initially the dry air will remain same, but the amount of water vapor which is collected at the bottom, it will be m dot a into difference in the specific humidity in between the inlet and the exit. So m dot a into omega 1 minus omega 2. So if you see, omega 1 is m dot v1 by m dot a minus m dot v2 by m dot a. So m dot a cancels. So it's just the difference between the mass of water vapors. So if you apply steady flow energy equation, so air is coming at m dot a into h1 plus there is some q heat which is rejected, and the exit is at m dot a h2 plus m dot w3 hw3. So this is the energy equation. Now dividing this by m dot a, so this is the specific sensible heat, and plus h1 equals h2 plus m dot omega 3, which you already calculated, so omega 1 minus omega 2 into enthalpy of water. So here we have to find out enthalpies, and you can substitute. So starting with the saturation pressure of water at 25 degrees Celsius and 15 degrees Celsius are 4.246 kilopascal and 1.705 1 kilopascal. So we know relative humidity, so from there we can find out your pressure, partial pressure of water vapor. So PV will be at state 1 will be 2.123 kilopascal and PV2 will be 1.3641 kilopascal. So now we know partial pressure, we know the total pressure. Now we can find out specific humidity. So omega 1 will be 0.622 PV by P minus PV. So substituting pressure values, we get omega 1 as 0.01331 kg of water vapor divided by kg of dry air, and omega 2 similarly is 0.00849 kg of water vapor per kg of dry air. Now we know specific enthalpies of water vapor and condensed. So HV1, so we know, we saw a previous problem how we calculate water vapor enthalpies. So we'll just take saturated conditions, say, which will be close, will not be very much. So at 30 degrees Celsius, the water vapor enthalpy, saturated water vapor enthalpy is 2556.3 kilojoule per kg. Similarly at 15 degrees Celsius is 2528.9 kilojoule per kg. So now we know both the enthalpy values, and so enthalpy at HW3 is 63 kilojoule per kg. HW3 is nothing but enthalpy of water at 15 degrees Celsius, which is 63 kilojoule per kg. That is saturated water, saturated liquid. Now substituting these values in the equation, substituting the enthalpy values, we will get Q as minus 27.3 kilojoule per kg dA, minus because we are losing heat. So we have found out the sensible cooling heat. So and the mass of water vapor removed, the moisture removed per kg is we know omega 1 and omega 2, it will be 0.01331 minus 0.00849 into mass of dry air, so per kg. So it will be a difference of this, which will be close to 85. 0.0048. So the mass of water vapor removed is 0.0048 kg of water vapor per kg of dry air. So the next question is, a 5 meter into 5 meter into 3 meter room contains air at 25 degrees Celsius and 100 kilopascal at a relative humidity of 75%. So determine the partial pressure of dry air, the specific humidity, the enthalpy per unit mass of dry air, and the masses of dry air and water vapor in the room. So we need to find out mass, enthalpy, and partial pressure and specific humidity. So what is given is Cp of air is 1.005, and for water at 25 degrees Celsius, the saturation temperature is 3.1698 kilopascal, and corresponding enthalpy of vapor is 2546.5 kilojoule per kg. Now we know saturated vapor pressure, which is 3.1698 kilopascal. So we can find out partial pressure of water vapor at so we know relative humidity and saturated vapor condition. So we can find out PV is 5 into saturated vapor. So 0.75 into 3.1698 will give me 2.38 kilopascal. Using this we can find out PA, the partial pressure of dry air, which will come out to be 97.62 kilopascal. So using this we can substitute it in specific humidity relation to find out specific humidity, which is equal to 0.622 into PV by PA. Substituting the pressure values will give me specific humidity as 0.0152 kg of water vapor per kg of dry air. So we have found out specific humidity, we have found out partial pressure of dry air, and the next is to find out enthalpy. So enthalpy is enthalpy of air plus specific humidity into enthalpy of water vapor. So enthalpy of air is Cp into T plus omega into sorry. So enthalpy of water vapor. So enthalpy of air is 1.005 into temperature is 25 degrees Celsius plus specific humidity is 0.0152 into enthalpy of water vapor is 2546.5. So substituting we find out that enthalpy is 63.8 kilojoule per kg of dry air. So the last is to find out the mass of each component. So volume is for both air and water vapor is same. So volume is 5 into 5 into 3, which is 75 meter cube. So using ideal gas equation, so m dot a is ma is pv by rt. So pressure, we know partial pressure of air, we know volume 75 meter cube, we know ra 0.287 kilojoule per kg Kelvin, and temperature. Substituting we get mass of air as 85.61 kg. Similarly for mass of vapor is 1.30 kg. The other way of finding mass of vapor is using specific humidity. So specific humidity is nothing but mass of water vapor divided by mass of dry air. So mass of water vapor is omega into mass of air, which is 0.0152 into 85.61 kg, which also gives me 1.30 kg. So both are same. So moving on, the next question is, we have a stream of moist air at 2 degrees Celsius dry bulb temperature and 80% relative humidity. This mixes with another stream of moist air at 30 degrees Celsius dry bulb temperature and 10 degrees Celsius dew point. The ratio by mass of 1 part of the first and 2 parts of the second. So 1/3 of mass of mixture is at 2 degrees Celsius dry bulb temperature and 80% relative humidity, and 2/3 is of 30 degrees Celsius dry bulb and 10 degrees Celsius dew point. So calculate and the temperature and specific humidity of the air after mixing. So for the first stream, we'll directly get values from the psychometric chart. So in psychometric chart, for corresponding to 80% relative humidity and 2 degree triable temperature, we can find out omega 1 as 0.0035 kg of water vapor per kg of dry air, and enthalpy as 10.78 kilojoule per kg of dry air. Now mass of dry air, so per unit of moist air we can find out. So m dot a1 will be 1 plus 1 by omega. So we know omega value, substituting we'll get mass of dry air will be m dot a, or mass fraction basically will be 0.9955 kg. So next is for the second stream. Similarly, for 30 degrees Celsius dry bulb temperature and 10 degrees dew point temperature, we can find out omega 2 is equal to 0.00765 kg water vapor per kg of dry air, and enthalpy is 49.67 kilojoule per kg of dry air. Similarly, we can find out mass of dry air at point state 2. Here this is 2/3, so we multiply it by 2, because previously this was first stream which is coming in 1/3, so this is 2/3. So for 2 units we will multiply by 2, so 2 by 1 plus omega 2 will come out to be 1.9848 kg. So for the mixture, we multiply m dot into h1 plus m dot into h2 divided by m1 plus m2. So enthalpy of the mixture will come out to be 36.68 kilojoule per kg of dry air. Similarly, omega is m dot into omega 1 plus m dot into omega 2 plus m1 plus m2. Similarly, that will also comes out to be 0.00627 kg of water vapor per kg of dry air. So we'll move to next problem. Moist air enters a chamber at 5 degrees Celsius dry bulb temperature and 2.5 degrees Celsius thermodynamic wet bulb temperature at a rate of 90 centimeter cubic millimeter. So the barometric pressure is 1.01325 bar. While passing through the chamber, the air absorbs sensible heat at the rate of 40.7 kilowatt and picks up 40 kg per hour of saturated steam at 110 degrees Celsius. So determine the dry and well bulb temperature of the leaving air. So this is the process. So air is entering at 5 degrees Celsius dew point temperature and 2.5 degrees Celsius wet bulb temperature. So the pressure is at 1 bar. So while passing, what will happen is you are initially heating the air, so there is sensible heating. After that you are injecting steam, so it will pick up some water vapor and it's coming out. So we have to find out the dry and wet bulb temperature of the leaving air. So what's happening is, this is the process in a psychometric chart. So at 1 to 2 is sensible heating around the coil. So where heater, you are putting a heater, so you are having sensible heating, your specific humidity is not varying, so you are just varying the increasing the temperature, so sensible heating, so 1 to 2. Then you are adding steam. In this case there will be heating as well as humidification, so 2 to 3 is the adding steam process. So now initially at 1 is at 5 degree dry bulb temperature and 2.5 degrees wet bulb temperature. So the correspondingly at that point your enthalpy is 13.82 kilojoule per kg of dry air and your specific volume is 0.792 and your omega value, specific humidity, is 0.0036. So this is what is known at state 1 from the psychometric chart. So now we know the air is entering at 90 cm, and we can find out m dot a. So you are finding mass of air, so we know specific volume, so we substitute that, we find out this is cubic meter per minute. Mass of airflow is 90 cubic meter per minute. So 90 into 60, we have to convert it into R, divide by specific volume. So 90 into 60 divided by 0.792 will come out to be 6820 kg of dry air per hour. This is the mass flow rate of air which is coming in. So from point 2 to 3, the mass of water vapor which is absorbed, it will be equal to m dot a into omega 3 minus omega 2 or omega 1. Omega 1 to omega 2 will be same. It will be equal to 40 kg per hour, which is given in the problem. Using this, we can find out omega 3, which will come out to be 0.00947 kg of water vapor per kg of dry air. So now by doing an energy balance, so m dot a equals h3 minus h1 will be equal to 40.7 into 3600. So this is 40.7 kilowatt. So into converting into kilowatt hour, we multiply by 3600 plus 40 is the mass flow rate of water vapor which is added in the as a steam into enthalpy of steam. So enthalpy of steam at 110 degrees Celsius is 2691.3. So substituting that, we can find out enthalpy at state 3. So enthalpy at state 3 is 51.1 kilojoule per kg of dry air. So from psychometric chart, we know now two values, enthalpy and specific humidity. So we can find out dry bulb and wet bulb temperature correspondingly. So the straight line, so that point will be equals to 26.5 degrees Celsius and 18.1 degrees Celsius. So we will take constant enthalpy lines and constant specific humidity lines. The where it meets will be state 3. So corresponding dry bulb temperature is 26.5 and corresponding wet bulb temperature will be 18.1 degrees Celsius. The next problem is a room for process work is maintained at 20 degrees Celsius dry bulb temperature and 25% relative humidity. So this is the condition required for the room. So the outside air is at 40 degrees Celsius dry bulb temperature and for 25 degrees Celsius wet bulb temperature. 12 cubic meter per minute of fresh air is mixed with the part of recirculated air and passed over the adsorption dehumidifier. It is then mixed with another part of recirculated air and is sensibly cooled in a cooler before being supplied to the room at 14 degrees Celsius. The room sensible and latent heat gains are 6 and 0.8 kilowatt. Calculate the volume flow rate of the air entering the dehumidifier and the amount of heat removed in the cooler. So the performance of the absorbent material is as follows. So this will give me the moisture content is how much is removed by the absorbent material, and the bottom is the heat of adsorption may be taken as 390 kilojoule per kg of dry air. Per kg of dry air per kg of the moisture absorbed. So we'll see how to solve this procedure. So this is the process. So you are taking some amount of air, this is 12 cm, and you are mixing it with some part of air which is coming from the room. So you are mixing this both and you are sending it to a dehumidifier, where you dehumidify and you mix it again with recirculated air. Mix it and you send it to a cooler, where you cool the air and you send it to room. So this should be a temperature of 40 degrees Celsius and 20 degrees Celsius and 25% relative humidity. So this is the whole process which is happening. So this is shown in the psychrometric chart here. So initially 0 is the outside condition, which is air available 40 and 15.5, which is specific humidity in grams per kg. So 40 and 25 degrees Celsius wet bulb temperature. So this is state 1, and your room air is coming at state I. So here, so this is at 20 degrees Celsius dry bulb temperature and 25% relative humidity. Now this both air are mixing and it's coming at state 1. Then 1 you are dehumidifying and cooling, dehumidifying and heating. So it comes to state 2. From state 2 you are mixing again with state I. So there it goes to state 3. From 3 you are cooling it, so it comes to state S, supply air, and then again it's going to state I. So now if you see, supply air rate is nothing but the total amount of Q which is removed divided by Cp delta T. So we know supply temperature, which is at 14 degrees Celsius, and we know that for the room sensible heat is 6 kilowatt and latent heat is 0.8 kilowatt. Using this we can find out mass of air which is supplied. So mass of air supplied is Q of sensible heat in room is m dot A Cp delta T. So we can find out mass of air using that. So Q of sensible heat is 6 kilowatt divided by Cp of air 1.0216 into delta T. You are supplying it at 14 degrees Celsius and the room is at 20 degrees Celsius. So 20 minus 14, which will come out to be 0.979 kg of dry air per second. Now the latent heat balance, using latent heat balance we can find out mass of specific humidity of air. So m dot A into omega I minus omega S into 2500 is the latent heat, equals latent heat load, which is 0.8 kilowatt. So using that we can find out omega I is 0.0033 kg of water vapor per kg of dry air. Now fresh air is thickness 12 meter cube per minute. So 12 divided by 60 to convert it into seconds, divided by specific volume of air, which is 0.91, which will come out to be 0.22 kg of dry air per second. So this is the amount of mass of air which is taken in. So So total recirculated air is m dot ai equals m dot as minus m dot ao. So amount of fresh air which is coming in is will be equal to amount of fresh air which is going out to have a mass balance. So air O, so mass of air which is recirculated will be 0.9799 minus 0.22, will come out to be 0.759 kg of dry air. So now we do mixing before dehumidifier. So m dot ao is air, fresh air into specific humidity of fresh air, plus m dot ai into omega I is the recirculated air, will be equal to mass of air, fresh air, plus mass of recirculated air into omega 1. So we know omega naught and omega I, we can find out omega 1. So using this, we don't know ma or I. The amount of fresh air going to the first, recirculated air, we recirculated is split in two parts. So the unknown is here is mass of air, the recirculated air, and omega 1. Similarly, mixing after dehumidifier. So here also we don't know the mass of air and the omega fraction. So here we substitute m dot a2 in terms of m dot a1 because we know total amount of recirculated air. So using equating these two, we can find out relation between omega 1 and omega 2. So using trial and error, we can find out omega 1 will be equal to 8.1 grams of water vapor per kg of DA, and omega 2 will be 1.96 gram water vapor per kg of dry air. So we have found out specific humidities. So now using substituting, we can find out the mass of air which is splitted and recirculated. So m dot a1 in the first stream is 0.366 kg of dry air, and m dot a2 is 0.393 kg of dry air. So using this, we can find out the mass of air which is flowing through the dehumidifier, which will be equals to mass of supply air minus air which is going out, will come out to be 0.759 kg of dry air. It will be m dot as minus m dot a12, so it will be equal to 0.586 kg of dry air. So now heat liberated due to condensation of moisture or in dehumidifier will be equals to m dot a into difference in specific humidity into HFG. So we know omega 1 and omega 2. Substituting that, we can get 9 kilowatt, and heat of absorption is m dot a into omega 1 minus omega 2 into 390. So per kg of water vapor, 390 kilojoule is absorbed, heat is ever. So that will come out to be 1.5 kilowatt. So the temperature rise of air in the dehumidifier will be, so 9 kilowatt plus 1.5 kilowatt of heat is added to the dry air, so equals to mcp delta T. So we can find out the temperature difference is 17.4 degrees Celsius. So the temperature of air entering the dehumidifier will be m dot a1 into Ti plus mass of air with fresh air into temperature of fresh air divided by total mass. It will come out to be 27.5 degrees Celsius. So the temperature of the air leaving the dehumidifier will be 27.5 plus 17.4. So it will come out to be 44.9 degrees Celsius. So now we know temperature at the exit of humidifier. So we can calculate the volume flow rate in the dehumidifier. So it will be m dot A into specific volume, which will come out to be 30.2 cmm. So similarly, after dehumidifier, after cooling, the temperature will be T3 m dot A T3 supply air equals to m dot A1 T1 m dot A1 T2 after temperature m. So basically here m dot A1 T2 plus m dot AI2 into Ti will be equals to m dot 3 into m dot S AS. So substituting the values, we can find out temperature at state 3, which is 34.9 degrees Celsius. So from psychrometric chart, we can find out the enthalpies at state 3 and state S. So the heat removed in the cooler will be mass of air supplied m dot AS into H3 minus HS, which will be 21.7 kilowatt. So that was asked in the question. Calculate the volume flow rate of the air entering in the dehumidifier, amount of heat removed. So I calculated both. So the next question is, last question is, we have an air conditioned space which is maintained at 27 degrees Celsius tribal temperature and 50% relative humidity. The ambient conditions are 40 degrees Celsius tribal temperature and 27 degrees Celsius wet bulb temperature. The space has a sensible heat gain of 14 kilowatt. Air is supplied to the space at 7 degrees Celsius, which is saturated. Calculate mass of moist air supplied to the space, latent heat gain of the space, cooling load of the air washer in kilowatt if 30% of the air supplied to the space is fresh, the remainder being series circulated. So the mass of dry air supplied to the space is Q dot S sensibility divided by Cp delta T. So Q is sensibility is 14 kilowatt into 3600 to convert into R divided by Cp is 1.02 into delta T is 27.7, 27 minus 7. So this will come out to be 2467 kg per kg of dry air. Ratio of moist air to the dry air in supply is 1 plus omega 2 is equals to 1.0062. So specific humidity is 0.0062. So at 7 degrees Celsius tribal temperature. So 1 plus omega 2 which is equal to 1.0062. So mass of moisture supplied to the space is 1 plus omega 2 into mass of dry air. So mass of dry air we have already calculated. So it will be equal to 2482 kg per hour. So now the latent heat gain of space will be equal to m dot A into difference in specific humidity into enthalpy of the water vapor. So 2467 into inside is 11.2 minus 6.2 specific humidity grams per kg of dry air. So divided by 3600 to convert it into R. Sorry, convert it into seconds, and divide by 1000 to convert it into kg into 2500 it will come out to be 8.57 kilowatt. So this is latent heat gain. So at point 1 we have mixing 70% said in the problem. So the cooling load of air washer in kilowatt if 30% of air supplied to the space is fresh and remainder is being recirculated. So 70% of recirculated air and 30% of fresh air. So T1 will be 0.7 into 27 temperature at room plus 0.3 into temperature of ambient, which is 40. This will come out to be 30.9 degrees Celsius. So at 30.9 degrees Celsius from psychometric chart, we will find out H1 as 64.9 kilojoule per kg of dry air, and cooling load of the air washer will be nothing but m dot A into H1 minus H2. H2 is 23, the supply temperature, and H1 is 64.9, and m dot A we have already calculated 2467. This will come out to be 28.71 kilowatt. So that's it for today. Thank you.